Hello, my name is Adam Larter. I'm a solutions architect at AWS, working with developers to help them understand how to build applications and systems using the components, tools and services of the AWS platform. In this session, I want to talk to you about building intelligent chatbots and voice bots using Amazon Lex, our natural language understanding service, and Amazon Polly, our service that converts text into lifelike speech. Think about the user interface in your own applications right now. They may have a fairly traditional user experience with search fields and text entry fields and buttons and dialogues. But imagine if your users could just chat to your application and ask it questions using natural language instead of clicking and swiping. Taking it further, imagine if your users could simply speak to your application, engaging in natural conversation using their own voice, as if speech was just another input device, another modality to interact with your application. Outside of web applications, speech interaction has fantastic utility in situations where users are focused on other tasks, like when they're driving or operating machinery. Sometimes it could be unsafe for typing and swiping and clicking on a user interface, but a voice interaction is much safer, easier, and simpler to use. Augmenting the user experience by adding additional modalities, like the ability for your user interface to listen, hear, speak, and understand intelligently, adds an extra dimension to your applications, and this is where chatbots and voice bots come in. Chatbots and voice bots allow your users to converse with your app as if they were talking to another person. These intelligent, multimodal interfaces make the interaction between your application and your users much more simple and engaging. Amazon Lex and Amazon Polly make it really easy to add chat and voice interaction to your applications, and we're going to see these services in today's examples. Today, I'll introduce the various concepts, controls, and features that Amazon Lex and Amazon Polly provide, and how to create and test your chatbot in the console. I'll show you how you can use Lambda functions that will hook into each voice interaction, allowing you to control the flow of the conversation programmatically. We'll take a look at the application logic that makes your Amazon Lex chatbot work, and how to manage the conversation context using session-based attributes. We'll see how to interact with our bot using text from our own website using the Amazon Lex API, or from a social platform like Facebook Messenger. And how we can use voice interaction to create a completely hands-free natural language experience for our applications. To demonstrate, I've created a fictitious startup that I've called TravelBuddy. TravelBuddy sells flights and accommodation at the last minute with massive savings for my customers. I've built a standard website that allows my users to register, log in, search for flights and accommodation, and to make reservations. My site is hosted on Amazon S3 as a single-page web application and might use a framework such as Angular or React, making RESTful calls for data served via Amazon API Gateway ahead of AWS Lambda functions that query Amazon Elasticsearch or Amazon DynamoDB. My site is serverless and serviceful, secure, scalable, and highly available. So let's take a quick look. Right now, I have a gadget to allow my users to quickly enter the destination that they're looking for, perform a search, and show various options and prices. The user would then click on an option to proceed with the reservation. To remove any usability friction and provide a more natural interaction, I want to implement a chatbot using Amazon Lex. Amazon Lex is a natural language understanding engine that is powered by the same deep learning technology as Amazon Alexa. We can use Amazon Lex to build chatbots for websites, integrate with social messaging platforms such as Facebook, Slack, Kik, and Twilio, and interact with our users via text or voice using the native integration with Amazon Polly. Key to building a successful conversational interface is an understanding of the Amazon Lex concepts: intents, utterances, slots, and fulfillment. Intents are what you mean or what you intend when you say something. For example, if I say, I want to book a hotel, the intention is that I want to book a hotel. An utterance is what you say that has meaning or intent. In the previous example, I want to book a hotel is the utterance that invokes the intent, book a hotel. There can be many utterances that have the same meaning, and so multiple utterances can link to a single intent. Slots are like variables or parameters that we need the user to provide values for during the conversational exchange in order to fulfill the intent. Slots have data types: time, date, location, etc., and you specify the type when you define a slot. Once we've elicited all the slot values, we are ready to fulfill the intent. Fulfillment is the last concept we need to understand. This is what we want to happen as the result of the interaction, and normally we would perform some task like updating a database or triggering a workflow. To make it easier to create your bots, Amazon Lex allows you to use a built-in library of intents. These provide pre-configured utterances for common actions that you need across all chatbots, such as asking for help using the help intent, or cancelling an interaction using the cancel intent. Amazon Lex also provides built-in support for commonly used data types such as city, date, and time. The built-in date type, for example, manages the complexities of absolute and relative dates, and dates with special meanings such as Christmas Day or New Year's Day. Amazon Lex handles the date calculations for us. Let's take a simple chatbot example. I've created an intent that I've called test intent and added some sample utterances. You can see how I've created a few variations that all map to the same intent. So I could say, I need a room, or I could say, I want a hotel. Those two utterances would trigger my test intent, but neither would provide any slot values. Lex will prompt the user for the value of the 3 slots that I've defined down here: destination city, check-in date, and room type. But I could also say, but also notice how I could say, I want a hotel in Melbourne. And that would match the sample utterance, I want a hotel in destination city. And at the same time, it would provide the value for the slot, destination city. I could also say, I want a hotel in destination city for check-in date and provide both the destination city and the check-in date at the same time. The slots I've defined each have types. Destination city is of type US city, which is a built-in catalogue of predefined cities. Check-in date is a date type and will allow the user to specify an absolute date or a relative date construct, such as tomorrow. Lex will handle the conversion to a usable date value for that slot for us. The last slot is room type. And notice how this is of type hotel room types. This is a custom slot type that I have defined. If I inspect the definition of the hotel room type's slot type, you can see I'm making use of a feature where I can map the possible slot values to synonyms. So here you can see that if the user says penthouse or premium or best in place of the room type, then Lex will map that to the value penthouse. So my application doesn't have to do that mapping by itself. Instead, I could ask Lex to expand the values, and this means that the values that I have provided are just hints to Lex. If the user says a room type other than one of these that I have defined, Lex will accept it as a slot value. So my application would need to handle any arbitrary value for that particular slot. It is completely up to me as the developer to decide which mode I would prefer to use. I've also set a confirmation prompt. When all the slot values have been provided by the user, Lex will respond with a confirmation prompt and expect the user to respond with a yes or no answer. In this case, Lex would respond, shall I go ahead and reserve your room type room in destination city for check-in date? And would replace room type, destination city, and check-in date with the actual values provided by the user. If the user responds negatively, Lex will respond with the cancel prompt. In this case, okay, no problem. Otherwise, when the user responds affirmatively, then Lex will fulfill the intent. In my test intent, I have set the fulfillment mode to return parameters to client. In this case, the client that is calling Lex will receive a JSON payload describing all the slot values. Let's see that in action. I can test the bot in the browser directly. If I say, I need a room, then the sample utterance without any slots will trigger the intent. Instead, I could say, I want a room in Melbourne for tomorrow, and provide both the destination city and the date at the same time. Amazon Lex will respond by prompting me for the missing value for the slot room type. Let's say I want the best room, and Amazon Lex maps best as a synonym for penthouse because of the slot resolution I configured for the room type slot type. Now I have all the slot values that have been elicited from the user. Amazon Lex will return the confirmation prompt, and you can see how the slot values have been inserted into the response. And the relative date tomorrow has been resolved to the actual date. In response to asking me if we should proceed to book the hotel, I say yes, and then the intent is ready to be fulfilled. Because I set the fulfillment type to return parameters to client, Lex will respond back to the caller with a JSON payload describing the interaction. Notice here we have all the slot values. Our application can make use of this data and process according to our business logic. I've integrated the chatbot into my Travel Buddy website as well, so I can have the same interaction on my own site. Again, if I say I want a hotel room in Melbourne for tomorrow, the bot responds by prompting me for the room type. And if I provide the room type, then Lex responds with the confirmation prompt and the interaction continues. Now we've seen the chatbot working in the Travel Buddy site, let's look at the architecture. Notice how we have the client website call directly to the Amazon Lex service. We use the AWS SDK for JavaScript in the browser to make use of a Cognito identity pool to vend scoped temporary credentials to sign our requests and keep things nice and secure, and then call directly into the Amazon Lex service. Using the AWS SDK, we can very easily call in to Amazon Lex to submit our user's chat text. First, we construct a params object that contains our chatbot details and the text from the user that we want to submit. We also provide a user ID, which allows Lex to keep state across calls and maintain a session for us. We then simply call the post-text method of the Amazon Lex runtime object. And when the callback completes successfully, we will have an object that contains updated session attributes and also a message in text format that is the response from Amazon Lex. We simply push the Amazon Lex response message into our chat window, which is just a simple floating window created using CSS. For TravelBuddy to book flights, we need to have more programmatic interaction during the conversation with the user to validate each of the steps. So to do that, I'm making use of the AWS Lambda integration with Amazon Lex. I let Amazon Lex determine the flow of the conversation based on the utterances and slots that I configured in the AWS console. But in the case of TravelBuddy booking a flight, I have a more complicated workflow, and so I want to be able to run an AWS Lambda function on each interaction. And also, rather than simply returning the slot values to the caller when the intent slots are all elicited from the user, I want Amazon Lex to call a Lambda function directly to perform the fulfillment. I can do this using code hooks. Code hooks allow you to customize the user interaction and conversation flow, validate user input during the conversation, and also allow Amazon Lex to directly fulfill the intent outcome using an AWS Lambda function. When I specify a Lambda function for an intent's code hook, every interaction will fire the specified Lambda function to allow it to intercept the current state of the interaction, validate slot values, change the flow of the conversation, and even allow me to transfer state between intents. The Lambda function is passed an event, a JSON payload, which contains the context about the user input, such as the name of the bot and the intent the user is currently interacting with, the current state of all the slots and the session attributes, and the input transcript so we can see exactly what the user said. The dialog code hook Lambda function can check the intent information such as the intent name, invocation source, confirmation status, and slot values to determine what functions it should perform next, including redirecting the conversation to elicit a particular slot value from the user or transferring to another intent. Now, typically, your Lambda function would inspect the state of the interaction, do some processing such as querying a database to validate state, and then direct Amazon Lex on what to do next by returning a dialog action in the code hook response. In the code hook response, your Lambda function must return a JSON payload containing some key items. First, the session attributes, which you may have updated during the processing of your Lambda function. The dialog action, which determines what Lex should do in terms of the conversation flow. And the current values of each of the slots, which again, you may have updated during your function based on your business logic. There are 5 different dialog actions that you can specify, each of which have a specific effect on the conversation flow. You can close the intent, which completes the interaction, and no further input is required from the user. You can specify a confirm intent action, which means Lex is now expecting yes/no from the user. You can specify delegate, which will cause Amazon Lex to decide what to do next, and this decision is based on the options you've specified in the AWS console. You can return elicit intent, which will change the conversation context across to a completely different intent if you need to, or you can remain in the current intent and redirect the conversation to ask the user for a specific slot value with elicit slot. So I can completely control the conversation flow dynamically using code hooks and Lambda functions. Now let's say I want the user to be able to ask, what's the weather like at a destination? And have Lex provide their user with a weather report. Okay, so far so good. Next, the user decides they want to know what flights are available to that destination. The same destination that they just asked about. That would require a different intent because they may ask, tell me what flights there are to get there. I don't want my user to have to re-specify the destination. I want the conversation context to transfer between the 2 intents. I can do this using session attributes. When a client calls Amazon Lex, app-specific information can be passed along as session attributes. Amazon Lex will pass the session attributes to the Lambda functions called by the bot, and the Lambda functions can make use of, add to, or update the session attributes. In the previous example, in the first intent for the weather report, I would save the destination the user wants to know about in a session attribute. Then, when the book flight intent is triggered, I would code the Lambda function to look for a destination city in the session attributes. This way, the bot doesn't have to ask the user for the city that they're interested in, and the conversation flows much more naturally. In TravelBuddy, I've done exactly this. I use a session attribute to store a JSON payload that contains all of the information I need across all of my intents, things like origin city, destination city, and number of passengers travelling. Now, any of my intents can populate those fields, and other intents can use the values if they need them, rather than asking the user again. If a field is not set when an intent is triggered, we can redirect the user to provide that value using the elicit slot directive. Let's take a look at the different intents in my Travel Buddy chatbot to see how the user experience is designed. We have a check weather intent, which has a single slot, the destination city. This intent allows the user to ask things like, what's the weather like in London? And notice that we use a dialog code hook to process the interaction, and that in that Lambda function, we query a weather API. And also we store the city that we're referring to in a session attribute collection as destination city. Other intents can now check to see if this variable is set and make use of it. We also have a news about destination intent that also wants access to the destination city. And the Lambda code hook that we've configured looks at the session attributes to see if we have a destination city set, and if so, uses that by default. Otherwise, it prompts the user to provide the city that they're interested in checking the news about. The bot also has a check flights to city intent, which manages the interaction to elicit the destination city, origin city, number of passengers travelling, and the flight number from the user. So let's look at this in action in our Travel Buddy chatbot. I can ask, what's the weather like in Cairo? The chatbot responds with a weather report, which it gets from the Lambda function that calls out to a weather API. The Lambda function also sets a session attribute to remember the destination city that the user is referring to. Next, the user wants to know what the latest news is from that city, so they ask, what's the latest news from there? Which is a different intent. Notice we didn't specify the city. The Lambda function assumes Cairo because of the session attribute we set in the previous check the weather intent interaction. Let's say the user reads the news report and is really convinced that they want to go to Cairo, so they say, I want to fly there, which is another utterance that maps to yet another intent. The dialog code hook Lambda function looks up the database of available flights to the destination city and shows the top 3 to the user, prompting them to select a flight number or make another query. This time we're in the same intent, and Amazon Lex is eliciting the remaining slot values from the user, the flight number and the number of passengers travelling, in order to build an itinerary. Next, the user can ask about their itinerary, and Lex asks them if they want to proceed with the booking. If they say yes, we proceed with the booking. We'll assume that some transaction takes place at this point to confirm the arrangements. Now, there's another aspect to consider here in terms of our travel website, and that is reach. The kind of customers that I want to engage with may not be the kind of digital citizens that search online for a travel website and then browse to it. They may prefer other digital channels like social platforms. Amazon Lex integrates natively with Facebook Messenger, Slack, Kik, and Twilio, and apart from configuring the link between the chatbot and the social platform, you don't need to make any changes to your chatbot. When you're targeting Facebook Messenger, Slack, and Twilio, you may want to include response cards. Response cards are additional metadata that can be returned in your dialog response JSON to describe lists of options and do things like embedding images and URLs. Social platforms like Facebook can make use of this data to return lists of options as buttons and can embed the images and link to the URLs you provide. These all work to make things much easier for the user to interact with your chatbot. Integrating your chatbot with Facebook, for example, is really straightforward. Check out documentation for the step-by-step process required to obtain the relevant tokens and keys from Facebook Messenger. Then, on the Amazon Lex side, select the Channels tab in your bot and configure the details, including the tokens and keys from Facebook. Then click Activate. Let's see the results in action. If I go over to my Travel Buddy Facebook page, I can send a message to my chatbot and interact with it. And you can see I can have the same interaction with my customers via my Facebook page as I can on my own website. I can ask, what's the weather like in Melbourne? And what's the latest news from there? I can tell my chatbot that I want to go there and see the flight details retrieved from my database via the dialog code hook Lambda function. You'll also notice how Facebook renders the response cards in Messenger, and these make it easier for my user to interact with the chatbot in this mode. The same conversation flow still works, transferring state between intents using the session attributes, and I don't have to change any of my code. Just configure the Facebook integration with Lex and you're done. Now, I mentioned earlier that Amazon Lex can interact with text as well as voice, and that you can build applications that allow users to speak and have Lex respond back using voice. Amazon Lex integrates natively with Amazon Polly, a service for converting text into lifelike speech. Amazon Polly is a fully managed text-to-speech engine that supports 52 voices across 25 different languages and offers really low latency, so you can build applications that respond using speech in real time. And what's great for developers is that once you render speech as a file, you can reuse that file as often as you like, including it in your application resources and shipping it with your application without having to pay any ongoing license fees. So what if I wanted to grow my travel company and include physical kiosks that could be placed in public spaces and allow passers-by to interact with it using their voice and completely do away with keyboard and mouse? Well, in this last demonstration, I'm using a Raspberry Pi as the compute platform for my kiosk. It has enough processing power and RAM for this simple task and is a great platform for prototyping projects like this. So my hardware kit is a Raspberry Pi with a microphone connected so I can capture speech from the user. Here are some of the key features that I wanted to implement in this prototype. First of all, I want it to run headless, so I don't want any physical interaction from the user, just their voice. So I need to implement a hot word to get the device's attention to begin a conversation. So for this, I'm using a toolkit called Snowboy. After the user has gotten the device's attention with the hot word, I then need to be able to determine when the user stops speaking, to process what they said. For this task, I'm using SOX, an open source utility for audio processing. To keep the latency really low, I'm going to stream the audio packets up to the cloud using AWS IoT, so data is transferred while the user is still speaking, rather than waiting for them to finish speaking before starting the upload. And for natural language understanding and converting text to voice, I'm going to use Amazon Lex and Amazon Polly. The way it works is, the device is always listening out for the hot word to wake it up. The user just says, "Hey travel buddy," to wake the device up, and it responds back to prompt the user to ask a question. I've used Amazon Polly to create the sound files with the prompts and ship them with the device so the voice remains constant whether the responses are predetermined like this one, or dynamic, which they will be for most of the conversation with the voice bot. The device then turns on the microphone to capture what the user says and streams audio chunks up to AWS in real time to the AWS IoT service. I am using AWS IoT as an MQTT endpoint to get really low latency from my device to the cloud to make the voice interaction as natural as possible. I have an AWS IoT rule that sets the audio chunks into the DynamoDB table for temporary storage. When the user stops speaking, the device detects silence using the SOX utility and then makes a secure call into Amazon API Gateway to trigger a Lambda function to reconstruct all of the audio chunks into a single file and pass it on to Amazon Lex for processing. Amazon Lex processes the voice interaction, runs my Lambda code hooks with their business logic just like it does with the text input from the chatbot. But since we're providing an audio input rather than text, Amazon Lex will use Amazon Polly to render a speech response as an audio payload. Amazon Lex returns the audio payload together with the other bot information like session attributes and dialogue action information, just like before. This goes back to the device, and we render the speech as an audio file and play it out the device's speaker. The whole interaction continues this way until the conversation is fulfilled exactly like it works with text. I don't have to make any changes to my chatbot in order to support this new modality. Let's see it in action. Okay, so what I have here is a pretty simple setup. I've got my Raspberry Pi 3, an analog speaker so I can hear what the device is saying, and a microphone to capture the audio from the user. So everything's up and running. Let's give it a try. Hey, travel buddy.
Hi there. How can I help?
What's the weather like in Melbourne?
The current weather for Melbourne is clouds. Overcast clouds. It is currently 19 degrees with a humidity of 64. Visibility is up to 10,000 meters.
And you can see here how I've got all the values from the JSON payload returned from Lex displayed on the screen, including the slot values. So let's say I wanted to know, what's the news from there? So I can say, hey, travel buddy.
Yeah?
What's the latest news from there? Notice how I didn't need to say the city name.
Here are the top 3 news articles about Melbourne. Patrick Allen reports, these are the safest major cities in the world to visit right now. David Lum reports, Amazon Australia starts taking orders. John Russell reports, Australia's Airwallex raises $6 million to grow its cross-border payment business.
Okay, I'm convinced. I really want to go to Melbourne. So I can say, hey, travel buddy,
Yeah?
I want to go there.
No problem. I've found 11 flights to Melbourne. Here are the first three by departure date. Flight 1048 from Canberra on 22nd of January, $419. Flight 113 from Sydney on 18th of February, $262. Flight 1116 from Singapore on 9th of April, $447. Any of these dates suit your travel needs? If so, just say the flight number. Otherwise, we can look for other destinations.
113. That's the flight from Sydney to Melbourne.
Okay, let's take a look at Flight 113 from Sydney to Melbourne. How many passengers are traveling?
There are 2 of us.
Okay, got it. I have added 2 seats on Flight 113 from Sydney to Melbourne to your travel itinerary. When you're ready, just let me know and I will confirm and process your booking.
So at this point, that data is held in session attributes. So my next step is to ask Travel Buddy to make my booking. Hey, Travel Buddy,
Yeah?
I want to confirm my itinerary.
Here's your travel itinerary. I have 2 seats on Flight 113 from Sydney to Melbourne. Do you want me to proceed with confirming this booking?
Yes, please. You can see how natural the interaction is.
Okay, I am now processing your itinerary. You will receive an email confirmation shortly.
And of course, just as before, the interaction will continue and processing will take place and a booking will be made. Let's assume that just happens in the background. So as you can see, I didn't need to make any changes to my chatbot itself. It is exactly the same interaction that I would have had with the text bot in my Facebook webpage, in my Travel Buddy website, or even on the AWS console. Thanks for attending the session today. I hope you found it really interesting and that it helps you think about how you can add voice and text to your own applications. If, after today, you're wanting to take your AWS knowledge to the next level, you have several options available to you. To gain more confidence and hands-on experience with AWS, watch our instructional videos and explore the self-paced labs. Additionally, you can attend our instructor-led classes led by qualified AWS instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Don't forget to validate your technical expertise with AWS and use practice exams to help you prepare for AWS certification. Please take the time to provide feedback on today's event so that we can improve the event experience for you in the future. I really look forward to seeing you the next time, and please enjoy the rest of the conference.